So next topic is type number of a control system. Type number of control system. So the type number of the system is specified for loop transfer function or a closed loop transfer function g of s and h of s. The number of poles of the loop transfer function lying at the origin decides the type number of the system. So for example, in general, the transfer function is represented as g of s into h of s can be written as k into p of s by q of s, numerator polynomial by denominator polynomial, which can be represented with some constant k, s plus the roots of the numerator polynomial is zeros, s plus z1, s plus z2, s plus z3, so on, divided by the roots of the denominator polynomial are poles, s plus p1, s plus p2, s plus p3, so on like this, where the term k is a constant, and here generally to mention the type number of the control system, the number of poles which are lying at the origin is deciding factor of type number of the system. For example, n is the number of poles at the origin. N is the number of poles at the origin. If you take a S plane, so here the number of poles which are lying at origin will decide the type of a system, type number of a control system. For example, if the value of n in the denominator polynomial of loop transfer function which is shown above decides the type of the number system. So if n is equal to 0, then that can be called as type 0 system. If n is equal to 1, that means if one pole is located at origin, that can be called as type 1 system. And n is equal to 2, similarly this can be called as type 2 system, and so on like that, type 3 and so on. So here the number of poles which are located at origin will give you type of the system, and total number of the poles in the denominator will give you order of the system. So here the number of poles which are located at origin will only give the type number of a system, but whereas if the number of poles which are lying in the denominator polynomial will give you order of the system. Next one is steady state error. So generally we will find the steady state error in the steady state component whenever the system is reaching to steady state. So here this is a system having the gain g of s, and this is the output c of s, and this is the input r of s. Then the feedback is given like this. Negative feedback is given. So here this is the error E of s between the input and as well as the sample of output which is fed from the output. So C of s into h of s, this is the signal which is coming from the C of s and multiplied with h of s. So let us consider this closed loop transfer function where R of s is the input signal and C of s is the output signal or a response, and E of s is the error signal, and C of s into h of s is the feedback signal. C of s and h of s is the feedback signal. So here the total or the error signal E of s is, from this block diagram, it can be written as R of s minus C of s into H of s. This is the error signal. Okay, so here the output is C of s, which can be written as E of s into G of s. So these two signals, multiplication of these two signals. Substitute this value here. Substitute this value here in this case, then C of s can be written as E of s substitute this value here, this output in this case. So here E of s can be written as R of s minus E of s into G of s into H of s. So therefore E of s plus E of s into G of s into H of s is equal to R of s. From this, take E of s as common, then this will be 1 plus G of s into H of s, which is equal to R of s. So from this, the error signal E of s can be written as R of s divided by 1 plus G of s into H of s. So this is a error signal in Laplace transform form, but I wanted to have the error signal in time domain system. So error signal in time domains analysis, in error signal in time domain can be obtained by inverse Laplace of this above signal. Error signal in time domain analysis is E of t, which can be obtained by doing inverse Laplace for this E of s. So here this can be written as E of t is equal to inverse Laplace of R of s divided by 1 plus G of s into H of s. Let ESS is called steady state error. ESS is called steady state error. Then the steady state error is defined as the value of E of t when the time t tends to infinity. So it can be defined as ESS can be defined as the value of E of t when time t tends to infinity, then only the steady state error can be calculated. So therefore steady state error can be written as limit t tends to infinity of E of t. So this is the steady state error definition. It can be defined as the value of E of t when the time t tends to infinity. So it can be written from the final value theorem. From the final value theorem, it can be written as, what is the final value theorem means? If f of s is equal to Laplace transform of f of t, then limit t tends to infinity f of t can be written as limit s tends to 0 s into f of s. This is the final value theorem. So if I apply this final value theorem to this, it is limit t tends to infinity E of t, which can be written as, so steady state error can be written as limit t tends to infinity E of t. This can be now written as limit s tends to 0 s into E of s, So here the steady state error can be written from this final value theorem as s tends to 0 s into E of s is nothing but R of s divided by 1 plus G of s into H of s. So this is the value of steady state error constant in time domain analysis. So we are having few static error constants here. So likely to be depending upon the type and number of a system, depending upon type number, depending upon the type number and input signal which we are giving to the system. So there are few error constants are there, likely to be positional error constant. Positional error constant, it can be represented with Kp, which is equal to limit s tends to 0 g of s into h of s. This is the positional error constant. And similarly, velocity error constant, Kv, which is nothing but limit s tends to 0 s into g of s into h of s. Next one, acceleration error constant, represented with Ka. Here it is limit s tends to 0 s square into g of s into h of s. So these are very important error constants: positional error constant, velocity error constant, and acceleration error constants, which can be represented with these formulas. So this Kp, Kv and Ka, or in general we can call them as static error constants. So Kp, Kv, Ka, we can call them as static error constants. Static error constants. So let us see the steady state error when the input is unit step signal. When the input is unit step signal, we have to calculate the steady state error. Steady state error when the input is unit step signal. Unit step signal. So steady state error formula is ESS is equal to, I am just taking final value theorem only, limit s tends to 0 s into r of s divided by 1 plus g of s into h of s. And we know that the input is step input, is step input. So therefore r of s value will be 1 by s. So therefore the steady state error constant can be written as limit s tends to 0 s into r of s is 1 by s divided by 1 plus g of s into h of s. So here this will be gets cancelled out, s and this s, and therefore it can be written as ESS is equal to 1 by limit plus limit s tends to 0 g of s into h of s. I am applying this limit to this entire function so that this will become now ESS is equal to 1 by 1 plus limit s tends to 0 g of s into h of s. So from the static error constant, we know that this limit s tends to 0 g of s into h of s, this can be called as Kp. So therefore steady state error constant ESS can be written as 1 by 1 plus Kp. 1 by 1 plus Kp. So where Kp is called positional error constant. And type 0 for type 0 systems, let us check for type 0 system, type 1 system. So type 0 system, type 0 system. So value of Kp for type 0 system is limit s tends to 0 g of s into h of s. So here g of s into h of s can be written as limit s tends to 0 k into s plus z1, s plus z2 and s plus z3 so on, divided by s plus p1, s plus p2 into s plus p3 so on, like this. So when limit s tends to 0, when limit s tends to 0, then this can be written as k into z1, z2, z3 divided by p1, p2, p3. So which is nothing but a constant, which is nothing but a constant. So therefore the error constant formula ESS can be written as 1 by 1 plus Kp. So where Kp is the constant here, therefore 1 by 1 plus constant is nothing but a constant. So in type 0 system, the conclusion is hence in type 0 system, when the input is step input, then the error constant is, then there will be a constant steady state error. Then there will be a constant steady state error. So this is the conclusion for type 0 system. So if we take type 1 system, then for the type 1 system, Kp is nothing but limit s tends to 0 g of s into h of s, same formula I am using. This for type 1 system it is limit s tends to 0 k into s plus z1, s plus z2, s plus z3 so on, divided by s, because it is a type 1, s power of 1 we have to take, s plus p1, s plus p2 so on. So here when you apply the limit, to this s tends to 0, then this will become k into z1, z2, z3 so on, divided by s tends to 0, so it is nothing but 0. Something into 0 is nothing but 0. So anything divided by 0 is nothing but infinity. So here Kp became infinity in type 1 system. And the steady state error formula, we know that 1 by 1 plus Kp, which is nothing but 1 by 1 plus infinity, which is nothing but 0. So likewise, if we take type 1, I got Kp as infinity and ESS as 0. If I take type 2, type 3, type 4, type like that, so on, whatever you take, you will get 0 steady state error constant. So the conclusion is system with type number 1 and above, for unit step input, the value of Kp will become infinity. And the steady state error value will become 0, and there will be 0 steady state error constant. So this is related to steady state error when the input is step signal.